Hi, I am B. Satyaiah, Assistant Professor of Mathematics in the Department of H&S, TKR College, Meerpet, Hyderabad. Today's my lecture is on applications of Cayley-Hamilton theorem. The Cayley-Hamilton theorem explains the connection between a matrix and its characteristic polynomial. One of the major uses of the Cayley-Hamilton theorem is to calculate the solutions of linear differential equations. It is also used in calculating the higher powers of matrices, characteristic polynomials of a matrix, and the inverse of the matrix. So let's get started. Here, the statement of the Cayley-Hamilton theorem is every square matrix satisfies its own characteristic equation. So, whenever we are having a square matrix, it satisfies its characteristic equation. So, the main uses of Cayley-Hamilton theorem is just one I explained to calculate the positive integrals of powers of A, that means higher order powers of A, and the inverse of non-singular matrix. So we'll discuss some applications of Cayley-Hamilton theorem, especially finding the characteristic equation and then finding the higher order powers and inverses. So one of the example is show that the matrix 1 minus 2, 2, 1 satisfies its own characteristic equation. So we have to prove this matrix satisfies its own characteristic equation. Since we are given A is equals to 1 minus 2, 2, 1. The characteristic equation of the given matrix is A minus lambda I equals to 0. And from that, we will get an equation like lambda square minus s1 lambda plus here there is a small correction. This is s2. Make it that note. So here where s1 is the sum of diagonal elements, that is here we are having 1 plus 1 which is given by 2, and S2 is the determinant of the given matrix. So, which is obtained uh, S2 is equals to mod 1 minus 2, 2, 1. From that, we are getting the determinant of this matrix is uh, 1 into 1, 1 minus of minus plus 2 into 2, 4. So we are getting the determinant is 5. So therefore, the characteristic equation is uh, lambda square minus 2 lambda, since we are getting S1 is 2. So 2 lambda plus 5 equals to 0. Now we are proving whether the given matrix satisfies this characteristic equation or not. Now, simply we are replacing in place of lambda the given matrix A. So we'll get A square minus 2A plus 5I, where I is the identity matrix. So we should prove this equals to 0. So now we required A square. So that is the reason we are calculating A square. So that A square can be written as A into A. Simply we are multiplying the same matrix. So first we are writing the two again A 2 times 1 minus 2, 2 minus 1, and 1 minus 2, 2 minus 1. Here, remember, multiplication is nothing but multiplying the each and every element with whatever the value we are multiplying. So here, first row multiplied with first column, and again we substitute that value, whatever the value will get in the first row, first column, first element. Similarly, remaining elements also. So here, by multiplying one. So here, multiplying these two matrices, 1 into 1 plus minus 2 into 2. So we are getting 4. 1 minus 4, we are getting minus 3. Similarly, next to 1 into minus 2, next to minus 2 into 1. So minus 2, minus 2, minus 4. So again, multiplying second row with first column, 2 into 1 plus 1 into 2. So 2 into 1 is, so we are getting 2 into 1 and next to 1 into 2. So therefore we are getting 4. Next to again multiplying the same row with second column, 2 into minus 2 is minus 4 plus 1 into 1 is 1. So we are getting minus 3 here. So we got a square value. Now we substitute this a square value in the above equation. If we are verifying whether we are getting 0 or not. So here again, a square we got just now, minus 3, minus 4, 4, minus 3. So we are writing in the above equation left hand side. So minus 3, minus 4, 4, minus 3, minus 2 into a, that is 1, minus 2, 2, 1, plus 5 into I. So we'll write 5 into 1, 0, 0, 1. So again, some of these, I mean, simplification of this, we are getting first matrix same as this, minus 3, minus 4, 4, minus 3. From the second one, we'll get, so here we are multiplying with minus to all the elements of the second matrix. So therefore, we are getting plus minus 2, minus of minus plus 4, next to minus 4, minus 2. And multiplying this 5 all the with the all the elements of unit matrix will get 5, 0, 0, 1. Sorry, 5. So now sum of all this means again sum of matrices is nothing but adding the corresponding elements in the each matrix. So here minus 3, minus 2, plus 5. First element minus 3, minus 2, plus 5. So minus 5 plus 5 gets cancelled, will get 0. Next to minus 4 plus 4 and plus 0, direct we are getting 0. Next to 4 minus 4 plus 0, again we are getting 0. Minus 3 minus 2 plus 5 equals to 0. So we are getting 0 matrix. Hence, we can say that our given matrix satisfying its own characteristic equation. So now we'll discuss one more application, which is yeah, uh, verification of Cayley Hamilton theorem, one more application. So here we need to find a power 4 and a inverse. When a is equals to the 3 by 3 matrix minus 2 -1, 2, -1, 2, -1. In the third row, 1, -1, 2. So that the solution of this matrix, for the given matrix, we have to find out by a fourth order, power 4, a power 4, and a inverse. So the characteristic equation of the given matrix is mod a minus lambda I equals to 0. From that, so since the given matrix is order 3, so we'll get a characteristic equation like lambda cube minus s1 into lambda square plus s2 into lambda equals to plus, sorry, there is a correction again, plus, uh, sorry. So we'll get alternate signs in the equation. So lambda cube minus s1 lambda square plus s2 lambda minus what you call s3, which is determinant. So here, this is the correct equation. Just to make it that corrections here, lambda cube minus s1 lambda square plus s2 lambda minus s3 equals to 0. So here s1 again, like previous our discussion, it is the sum of all diagonal elements. Okay? Sum of diagonal elements, that means -2 plus 2 plus 2. So that is again, there is a small correction. Here it is plus 2. So here and S2 is nothing but sum of the measures of the main diagonal elements or leading diagonal elements. That means we have to calculate the determinants of corresponding elements of main diagonal elements. So here the major or else minor of the first element is just to removing these first row and first column, we'll get the determinant of matrix 2 -1 -1 2. So that is first element minor, and again similarly second element minor is again removing this column and row, we'll get -2, sorry, +2 2 1 2. So that is your second minor, and third minor simply removing last row and last column, we'll get again the determinant of 2 -1 -1 2. So those are the minors, and some of those gives your S2 value. That is here the determinant of 2 -1 -1 2 is 4 minus of minus plus. So we'll get 4 -1 plus 2 minus, sorry, 4 -2 plus here 4 -1. So we are getting 3 from the first part, next to plus 2 from the second part, and 3 from the third part. So the sum of 3 plus 2 plus 3 is 8. So we are getting S2 value 8. Now S3 is simply the determinant of given matrix mod A is equals to, again from the given matrix, make it the correction here. This is positive 2 only. So 2 into removing the first row and first column, the determinant of this one is 4 -1. Here we are getting that. Next to minus in the formula, and again we are having -1. So we'll get minus of minus plus 1 into, again removing the column and row, we'll get 4 -2. So here 4 -2. Next to again last element, that from that we'll get -1 2 and 1 -1. So there again 1 -2 will get. So therefore the determinant is equals to 3. So hence, by substituting all these values in the equation, we'll get lambda cube minus in the formula. We got 6, S1 value is 6 into lambda square plus S2 value just now we obtained 8 into lambda minus S3 value is 3. So which is equals to 0. This is our characteristic equation. There is another way to calculate the characteristic equation, that is in place of a minus in the a minus lambda I, simply we multiply the value uh, by using characteristic equation. So there is another way is also there. If possible, we'll discuss later. So now by Cayley Hamilton theorem, every square matrix satisfies its own characteristic equation. Again, we verify that is here's uh, the equation is a cube minus 6a square plus 8a minus 3I equals to, we should get 0 matrix. So we require again a cube, the higher powers. So that is the reason we are multiplying again a into a, that is a square. Again multiplying the given 2 matrix. After simplification, we'll get this matrix, 3 by 3 matrix, 7 minus 6, 9, minus 5, 6, minus 6, 5, minus 5, 7. And we require a cube. So therefore, we are multiplying a square and a, or else a into a square. We get again, after simplification, 29 minus 28, 38, minus 22, 23, and minus 28. In the last row, 22, minus 22, 29. So now we are verifying whether the LHS equals to RHS or not. So in the above equation, we are having a cube minus 6a square plus 8a minus 3I, where I is the identity matrix. Okay, so substituting all the values from the above. So here a cube is just now we obtained first row having 29 minus 28, 38. Next to second row minus 22, 23, minus 28. Third row 22, minus 22, 29. Next to minus 6 into again a square value is 7 minus 6, 9. So substituting all these values in the place of a square. So that is minus 6 into 7, minus 6, 9, the first row elements. Second row elements are minus 5, 6, minus 6, and third row elements are 5, minus 5, 7. Next to plus 8 into a, that is given matrix, we substituted here. Next to minus 3 into unit matrix, identity matrix with order 3, that is 1, 0, 0. Second row 0, 1, 0, third row 0, 0, 1. Now sum of all this, we get first row, first matrix same as it is, second matrix multiplied with 6, means each and every element should multiply with 6. So 6 for 7 are 42, next to 6, 6 36 with negative sign, and 6 9 are 54, 6 5 are minus 30. Here we are having minus 5. Next to yes, 6 6 are 36. Next to minus 6 into 6 minus 36. Third row 6 5 are 30. Minus 6 into minus 5 is minus 30 again. Next to 6 7 are 42. Next plus 8 into again each and every elements are multiplied with 8. So therefore we are getting 8 into 2. Again make it correction here plus 2 only. So 16, 8 minus 1 into 8 is minus 8. Again 2 into 8 is 16. Second row minus 8 plus 16 and again minus 8. Third row 8 minus 8 and 16. Next to minus, multiplying each and every element with 3, we'll get 3 0 0 in the first row, 0, 3, 0 in the second row, 0, 0, 3 in the third row. So again, sum of all this means we have to add corresponding elements in the each and every matrix. So here we are having 29 minus 42 plus 16 minus 3. So here minus 42 minus 3, that is minus 45. 29 plus 16 is 45. So 45 gets cancelled. We'll get 0. Similarly, remaining values minus 28 minus 36. 28, 20, 30, 50 and plus 8, 6, 14. So 64. Here, sorry, here we are having negative sign. So minus 28, minus of minus is 36. Here minus 8, minus 28, minus 8 is 36. Again, we are getting plus 36. Minus 36 plus 36 gets cancelled. We are getting 0. Next to 38 minus 54. Next to here plus 16. 38 plus 16. That is again 54. We are getting minus 6 to 54, both gets cancelled, we are getting 0. Similarly, all the values are vanishes, simply we are getting 0 matrix of order 3. So hence we can say that our given equation, our given matrix satisfies its own characteristic equation. So now we are also we have to find out the higher order power, like in the question given we have to find out a power 4. So from the given equation, I mean whatever we obtained by using characteristic equation. So here we are having the equation 2, I mean sorry, equation 1 as a cube minus 6a square minus 8a plus 3i. So equals to 0. Here equals to 0. So pushing all these values right side and multiplying this equation with a, will get a power 4 is equals to. So pushing these values to the right side, we'll get here negative 1. Pushing to the right side, we'll get positive. So already we'll get 6a square. Again multiplying with a, we'll get 6a cube. Again here uh, this is the equation. So there are some corrections here. 6a cube. Here we should get plus only. Pushing to the right side. Again, this one is also negative. Okay. Negative. So multiplying with a, we'll get a power 4 equals to, after simplification, 28a square minus 45a plus 18i. So again, already we are having a square value, a value, and I value also. Simply substituting all these values from the above in the above equation 3, we'll get a power 4 equals to 28 into a square is this matrix, and again minus 45 into given matrix A plus 18 into our unit matrix or identity matrix of order 3, 1 0 0 0 1 0 0 0 1. So again multiplying, and after simplification we are getting the matrix A power 4 is 124 minus 123 and 162, and second row minus 95 96 minus 123. The third row 95 minus 95 and 124. Now we are finding A inverse by using our characteristic equation. Since we are having the characteristic equation, that is A cube minus 6a square minus 8a plus 3i equals to 0. So simply again multiplying with A inverse on both sides of equation 1, in place of 3, I will get minus 3 into A inverse. Again, just to pushing this value to the right side, we will get 3A inverse is equals to A square minus 6A plus 8I. So here in place of A, we are getting I, since we know that A into A inverse equals to I. So we'll get I here. So from that, after substituting all these values a square and a value and I, after simplification, we'll find out a inverse. So substituting a square value, the matrix from the above, and again minus 6 into, I mean, simply multiplying the matrix with minus 6, we'll get minus 12, minus 1, minus of minus plus 6, next to minus 12, next to minus into minus plus 6, next to minus 12, next to minus of minus plus 6, third row minus 6 plus 6 minus 12, and multiplying this last matrix, identity matrix with 8, we get 8 0 0 0 8 0 0 0 8. So now 3A inverse equals to sum of these matrices. After simplification, we are getting 3 0 minus 3, 2 0 minus 1 1 3. So from that, we are getting A inverse equals to 1 by 3 into 3 0 minus 3 1 2 0 minus 1 1 3. So this is the process of finding inverse and higher powers also. Higher powers of given matrix here. So let us see one more application. So here the question is, find A inverse if A is equals to 1, minus 1, 4, 3, 2, minus 1, 2, 1, minus 1 by using Cayley Hamilton theorem. So again, we have to find out characteristic equation of the given matrix, that is mod A minus lambda I equals to 0. That is, so since our given matrix is 3 by 3 order, therefore we'll get the characteristic equation as lambda cube minus s1 into lambda square plus s2 into lambda minus s3 equals to 0. Again, where S1 is the sum of all main diagonal elements or leading diagonal elements. Next to S2 is minus of all these diagonal elements, and S3 is the determinant of given matrix. So S1 is sum of diagonal elements is 1 plus 2 plus minus 1. Simply we'll get 2. And S2 is minus of these diagonal elements. So that is first two main diagonal element minor is just removing the first row and first column. We are getting the determinant of 2 minus 1, 1 minus 1. So that is the first element minor plus second element minor is simply removing this column and row. We'll get 1 4 in the first row, in the second row 2 minus 1. This is the minor of second element. Next to minor of third element is just removing the last row and last column. We'll get the determinant of 1 minus 1 3 2. So these are the values we are getting. So from those determinants, so from the first part, we'll get minus 2 plus 1 plus next to minus 1 minus 8 plus 1 into 2 is 2. Next to minus of minus. So here we are having minus, and in the formula again we'll get minus. So minus of minus plus 3. So totally minus 2 plus 1 is minus 1. Next to minus 1 minus 8 minus 9. Next to 2 plus 3 is 5. So here we are getting minus 10 plus 5. So the sum of the minors of all diagonal elements is minus 5. That is our S2 value. Next to S3 is determinant of the given matrix. So the given matrix determinant is determinant of first row elements are 1 minus 1 4, second row elements are 3 2 minus 1, third row elements are 2, 1, minus 1. So therefore, we are getting the determinant 1 into just removing the row and column, we'll get minus 2 plus 1. Next to minus in the formula, again we are having minus 1, so we'll get plus 1 into removing the elements of second column and first row, we'll get 3 into 1 minus 3 minus of minus plus 2. So minus 3 plus 2, and again third, the third will get we remove uh, last of first row and last column, will get 3 into 1, 3 minus 2 into 2 minus 4. So the simplification is 1 into minus 1 plus 1 into minus 1 plus 4 into minus 1. So we'll get minus 1, minus 1, minus 6. Sorry, minus 4. So the sum of all this is minus 6. Therefore, we got S3 value is minus 6. So therefore, substituting all these values S1 and S2, S3 in a characteristic equation, we are getting lambda cube minus 2 lambda square minus 5 lambda plus 6 equals to 0. So now we verify whether the given matrix satisfying its own characteristic equation or not. For that, we simply replace in place of lambda the given matrix A. We are getting the equation like a cube minus 2a square minus 5a plus 6i equals to 0, where I is the identity matrix with order 3. So now our question is to find the A inverse. So here simply in the above equation we are having 6i. So simply multiplying the above equation with A inverse, we will get in place of I A inverse, and again we know that A into A inverse equals to I. Simply in place of A we are getting I. So therefore and A cube reduced to A square. So A square minus 2A and minus 5i plus 6 inverse. From this equation, just to pushing all these values to the right side, we'll get 6a inverse equals to minus a square plus 2a plus 5i. So from that, we will get a inverse equals to 1 by 6 into minus a square plus 2a plus 5i. So substituting a square value, a value, and I value, so we should substitute these values. So we required a square. So we are finding a square, that is a square equals to a into a. Simply multiplying a 2 times, we get a square. So that is a into a. So after simplification, we'll get 6, 1, 1, 7, 0, 11, 3, minus 1, 8. So in the right hand side of your equations 2, we are having the matrix with minus a square plus 2a plus 5i. So we are calculating that. So simply we are getting, after simplification, 1 minus 3 7 minus 1 9 minus 13 1 3 minus 5. So from that we are getting a inverse equals to 1 by 6 into 1 minus 3 7 first row, second row minus 1 9 minus 13, third row 1 3 minus 5. So where inverse is 1 by 6 into the matrix 1 minus 3 7 minus 1 9 minus 13 1 3 5. That is our required inverse. Now we'll discuss some more problems like use the Cayley-Hamilton theorem to find the value of matrix given by first two, f of a is equals to so and so. And second one, we have to find out a power 8 minus 5a, a power 7 plus 7, so on, by using a is equals to the 3 by 3 matrix 2 1 1 0 1 0 1 1 2. So again, as usual, we have to verify whether the given matrix satisfies so and so, and then by using Cayley-Hamilton theorem, we can find out all these two parts. So here, the characteristic equation of the given matrix is A minus lambda equals to 0, which is given by lambda cube minus s1 into lambda square plus s2 into lambda minus s3 equals to 0, where s1 is the sum of main diagonal elements, that is 2 plus 1 plus 2, that is 5. S2 is the sum of minus of the main diagonal elements, that is again from the given matrix, just to removing the first row and first column, we are getting first element minor 1 0 1 2, and again second element minor is removing this column and row, will get 2 1 1 2, that is second minor, and the third element minor is just removing the last row and last column, we'll get 2 1 0 1. So these are the three minors from the above matrix. So here again, the determinants of these three parts is 1 into 2, 2 minus 1 into 0 is 0, plus 2 into 2 is 4, minus 1 into 1 is 1. So 4 minus 1, plus 2 into 1 is 2, minus 0 into 1 is 0. So we are getting 2 minus 0, plus 4 minus 1, plus 2 minus 0. So we are getting 2 plus 3 plus 2. So we are getting 7. So S2 value, that is given by 7. Now, it is not required. So just to make it the correction, it is not required. So now we'll calculate S3 value, that is simply the determinant of our given matrix. That is 2 into the determinant of this matrix 2 by 2. 1 2 1 2s are 2 minus 0, next to minus 1 into, here removing this column and row, will get 2 0 into 2 0, minus 1 into 0 is 0, plus last element, so removing the first row and last column, will get 0 into 1 is 0, minus 1 into 1 is 1. So 2 into 2 is 4. Here we are getting 0, next to plus. Here we are having 1 into minus 1, minus 1. So 4 minus 1 is 3. So simply we substitute S1, S2, S3 values in the above characteristic equation. We'll get lambda cube minus 5 lambda square plus 7 lambda minus 3 equals to 0. So again, by Cayley-Hamilton theorem, we get simply substituting in place of lambda the given matrix A. We are getting a cube minus 5a square plus 7a minus 3i equals to 0. So from that, we require to find f of a is equals to a power 8 minus 5 a power 7 plus 7 a power 6 minus 3 a power 5 plus a power 4 minus 5a cube plus 8a square minus 2a plus I. And the second one is, we are assuming g of a is equals to a power 8 plus second. Yeah, second one is same like our first part. So we are assuming that only variation here. First one same as is e power 8 minus 5 a power 7 plus 7 a power 6 minus up to here minus 3 a power 5 is same as it is. Only where the variation here we are getting 8 into a power 4. We have to observe the each and every term. Next to minus 5a cube plus 8a square minus 2a plus I. So simply sometimes we don't observe these coefficients. So simply we can say that both are same. So we'll stop in the finding the second value. So we have to observe whether the two function values are same or not, and the coefficients also we have to observe. So here the coefficient of a power 4 is varies compared to first part. That is the reason we are discussing the second part also. So here from the above equation, by substituting the a in the characteristic equation, that is equation 1, so we are getting a cube minus 5a square plus 7a minus 3i. The equation, whatever we are having in the above, just dividing with, we are getting a power 8, so and so we are writing here. This dividing this equation with a cube minus 5a square plus 7a minus 3i. Just first one, we are having a power a simply. That is the reason we are multiplying. I mean, we are multiplying the give equation 1 with a power 5. We'll get a power 8 minus 5 a power 7 plus 7 a power 6 minus 3 a power 5. So after subtracting, all these values are vanishing. Simply remaining part we will get here a power 4 minus 5a cube plus 8a square minus 2a plus I. So we remain I same as this. We are writing up to here only. So next to plus a, we are getting, I mean, multiplying with a, the given equation, simply like your division of algebraic expressions. Okay, so we are using that method. So here we are getting a power 4 minus 5a cube plus 7a square minus 3a. So subtracting that, the first two terms are vanishing, and 8 minus 7, we are getting a square. Next to uh, here the signs are interchanging. So here we will get plus. So what do you call? The 3 minus 2 is 1. So plus a plus 1i. So again, so the given equation expressed as a cube minus 5a square plus 7a minus 3i into a square plus a plus here the remainder a square plus a plus I. So, which is simply we know that this is from a Cayley-Hamilton theorem. This part is equals to 0, and 0 into this part a square plus a is also vanishing. Okay, simply this total part is 0, plus we are getting a square plus a plus I from the remainder part. So therefore, we are getting f of a is equals to a square plus a plus I. So here we required a square. So multiplying given a 2 times, where after simplification we are getting a square value, that is the matrix a square is equals to 544010445. So substituting that a square and a and I value in the above equation 2, we are getting 544 next to 010,445 plus given matrix A is 211,010,112 plus the identity matrix of order 3 100,010,001. So after simplification, we are getting 855,030,558. Similarly, the second part we are calculating again by division algorithm. We are having the characteristic equation a cube minus 5a square plus 7a minus 3i. So we are having the power 8 onwards. So we are multiplying a with a power 5. We are choosing a power 5 in the quotient. We will get a power 8 minus 5 a power 7 plus a power 6 minus 3 a power 5. So after subtraction, these two gets cancelled. We are choosing the second part, that is here we are having in the second part here the quotient missing here, that is a correction. 8 will get here. So 8 a power 4 minus a 5a cube plus 8a square up to minus 2a we are writing. So again here we are having a power 4, but in the given obtained characteristic equation we are getting only a square. So therefore we are multiplying with we are multiplying with uh, 8a will get, sorry, we are having a cube. Okay, I forgot that. So a cube minus 5a square plus 7a minus 3i. So simply by multiplying with a, we'll get our record a power 4. So we are choosing 8a. So we'll get 8a power 4. Next to minus 40a cube. Next to plus 56a square minus 24a. So after subtraction, we'll get, so here positive, we'll get positive sign here, negative, positive, negative, positive. So here 8a power 4, 8a power 4 gets cancelled. We'll get 40 minus positive 40 minus negative 5. We'll get 35 a cube. Next to 56 with a negative sign plus 8. So 6, okay. Yes, so here a small correction, make it that. And next to again plus 24 minus 20 minus 2 will get plus 22, and again writing 1 into I here, we are getting 35 a cube here. After simplification we'll get 175 a square plus, here we are getting this one, and again choosing 35i with in the quotient multiplying with the given obtained equation, we are getting 35a cube minus 175a square plus 245a minus 105i. So after simplification, we are getting 127a square minus 223a plus 106i. So again, g of x from your division algorithm, from the division algorithm, g of a is, it can be represented as a cube minus 5a square plus 7a minus 3i. This is from your character, from the characteristic equation, and this is quotient plus this is a remain part. So as usual, we know that this first part, whatever we are having from the Cayley Hamilton theorem, which is equals to 0. So therefore, 0 into something, this part is also vanishing. Simply we'll get remainder term 27, 127 a square minus 223 a plus 106 I. That is g of a, we are getting 127 a square minus 223 a plus 106 I. Again, we are having already a square value, simply we are substituting here. So 127 into 5 4 4 0 1 0 4 4 5 minus 223 into a value is 2 1 1 0 1 0 1 1 2 plus 106 into identity matrix 1 0 0 0 1 0 0 0 1. After simplification, we are getting g of a value. In a similar manner, we can find each and every applications like finding the higher order and simplifying the given expression, and also we can find the inverse of the matrix. 1 second.